Thank you very much. The talk is about reducing delivery costs by optimal multi-CDN traffic allocation. It comes from a group of authors from Brightcove, and I'm Yuri Reznik. And we're talking about multi-CDN delivery, and you all know that it's a big topic. There are research reports published by EBU, many analysts saying that if you're big enough, you should really start using multiple CDNs. There are multiple activities across multiple industry forums, DASH-F, CTA Wave, SVTA. And when we talk about multi-CDN deliveries, there are multiple utilities that I usually mentioned. If you deliver in multiple regions, it becomes super useful. If you want to reach better scale, do load balancing. One single CDN is not good enough, it's useful. Improving reliability, failover in case one CDN fails is useful. And of course, improving QAE, QS is useful as well. But can, in principle, the use of multiple CDNs be cheaper than using a single one? And that's the question that I'll try to answer in this talk. The intuitive answer to this is no. If you have two CDNs and one of them is cheaper, just use the cheaper one. Even if they come with different rate ladders, splitting the bandwidth between them two in one range is not going to make delivery any cheaper. So this whole talk can stop here. If all you're looking for is cost of CDNs, there is no basis for any gains. But let's take a look at this problem a little longer. And let's look not only at CDNs, but also at origin servers. And if you look at origin servers, what we need to realize is that they also pull some traffic. And this some traffic comes as product of traffic at the end at edge cache times the probability at which CDN is missing. Cache miss probability. I denote them as P sub A, P sub B, and of course, the products of those probabilities times edge traffic becomes the traffic at the origin. And then if we look at cost models that are typically in place for CDNs and origins, we realize that origins are usually more expensive. They both can be modeled as some sort of piecewise constant functions. The more traffic you throw, the cheaper it becomes. When we talk about origins, the cost usually includes the cost of egress traffic, compute costs. If you use elastic load balancer or something else of this kind, you're going to have extra costs of cloud platform is doing, for example, dynamic transmax or encryptions, which typically done at origins, and so on. So they're more expensive. And then if we look at full costs, then we'll, of course, include the cost of CDNs at the edge plus cache miss probabilities, costs of the origins, and or we can equivalently talk about rates by normalizing everything for edge volume. And then let's take a look at this again and try to figure out which of the pathways will be cheaper. So the pathway includes the CDN plus origin it connects to. And for simplicity, let's assume that origins have same costs. I denote them by R sub O, and these are the expressions for total costs or total rates going along each pathways. So if you try to compare them and say that let's pathway A be less expensive, what it all boils down to? It boils down to this expression. It says that the difference between cache miss probabilities of CDN B times minus CDN A should be less than this funny ratio, which I denote by letter C. It's essentially cost disparity of the CDNs divided by the cost of origin. And to make it more intuitive, let me throw a few examples. So here I'm looking at cases when CDN A is cheaper and has worse cache performance, in which case, of course, the cheaper pathway will be CDN A. Opposite case will be CDN A is more expensive and has worse cache performance, so of course, CDN B will be less expensive. But the cases in the middle are actually most interesting. So this is the case when a CDN A is less expensive, but it has worse cache miss performance. And now it depends on what is the difference between cache miss probabilities. Remind that in situations when it's less expensive, but it actually costs more in a complete equation based on this inequality. And similarly, It could be less expensive, but it could have more expensive, but it could have better cache miss probabilities, and in composition, it's actually a cheaper pathway. So as we can see, this problem becomes more rich. We now have some basis for non-trivial solutions, and the key to all of this turns out to be not only the cost of CDNs, but also their cache performance. What is the cache miss probabilities that we see? But now you will say, wait a second. If this is a cache miss probabilities, how do I know it? And what it depends on? Well, it turns out one of the factors that influences the most is just popularity of content. If content is very popular, has very high hit rate, it's going to be cached with higher probability. It's a fundamental fact. It's how all paging or caching algorithms been designed since the 70s. In fact, the very first paper I'm citing here is just absolute gem. If you're interested in computer science, absolutely, please read it. It's first analysis of LRU algorithms, 1974. But in any case, phenomena is simple. The highest is the cache rate, the more likely is the content's going to get cached, but then you will say, but this must be affected by some other factor. So it will be different for different CDNs and different regions under different load. Yes, it will be, but we can model it. And we can model it in parametric form, and I'll show two very simple expressions. Please don't use them in product right away. It's mathematical expressions, but they still show the phenomena. And so in this case, V denotes access frequency, for example, number of hits per hour or per day. P are cache miss probabilities, V sub A, V sub B are CDN-specific constants, and gamma is a shape parameter. And this is a couple of examples where CDN A is worse than CDN B. It has a worse cache miss, but then based on parameter gamma, the shape could be either shallower or sharper. So if the CDN has ideal cache, it will just turn in a step function, a so-called classical static cache model. But of course, if it's real cache, it will be there will be some transition bands there. And this model captures it. And morale here is this. What this model tells us. If the content is very popular, it's going to get cached, and even worse, CDN at some point will be able to keep it. And if content is not popular, if being pulled once a year, well, it doesn't matter how good your CDN is. It's going to be pulled from origin. Now, let's take a look at this problem again now that we know this model, and let's try to turn this into bounds for popularity, content popularity. So again, same model, we're looking at same question when CDN A is cheaper. And before we just said that based on cache misses, it will be cache miss probability, it will be that inequality. Now, if we translate it to content access frequencies, turns out that solution becomes richer. There are ranges when CDNA is always cheaper. There is a condition when CDNB is always cheaper. And then there are two solutions in between where CDNA is cheaper, but then content frequencies should be either in one band or it should be at two ends of it. And let me give you an example. So if we put gamma 2, it's a shape parameter, the solutions become analytical. It's a simple biquadratic equation. And then I'm showing the solution of it at the bottom plot. So the horizontal line is that C, and the bell curve is now the shape of difference between cache miss probabilities. And you can see that it goes below that bar in two regions marked pink. So solution here says that your content needs to be either long tail or it has to be extremely high frequency accessed for CDNA to be more efficient. And what this means, if we're building a VOD system and we build VOD system with big catalog, well, with big catalog, you will see something like this. If you order content by popularity, you'll see that it will decay. This is classical zip for, in unbounded case, Z distribution model. It works well, for example, for YouTube videos, for many other cases. And same solution we've seen before can now be translated not to content access probabilities, but the indices of content. So for example, in this case, with all same parameter, we can see that for this catalog, with this distribution, what you really need to send to CDNA is first 3 items and then the rest of them in the tail. And that will be the best use in this case, and for the rest of them, just use CDNB. Again, this is an academic example, but I hope it gives a gist of the phenomena. And of course, with more complex models with different overlaps, the split becomes more intricate, and there will be more modes in that solution space. But now how to build it overall, what is the overall optimization problem? The rest is actually very simple. You look at the system, you bring full models, and then if you have a catalog, you just find that optimal split such that the sum of costs going along both pathways with the split of content is the minimum. And it's a basic constraint optimization problem. This formulas below show what each of the functions inside of the optimization problem is, and with a little bit of effort, it's actually solvable and turnable into a product. So during break, please stop by. I'll show you the demo if you're interested. And what we're doing is basically we're building system based on content steering mechanism, as was presented earlier. We push the steering logic all the way to the edge, but then there is a module that does all these optimizations and decisions on optimal split, and of course it pulls analytics data from analytics system, and it uses the logic to do the optimal content and allocation to minimize the cost of streaming. So with these conclusions, multi-CDN delivery is real. It helps in many ways, but remarkably enough, it also helps to minimize cost if you know how to manage the allocation of content, and if you have diversity between popularities of your content in your catalog, and also you have sufficiently different CDNs. Of course, there are some small challenges. You need to implement all of this. The problem is a little tricky, but with a little bit of effort, it actually works. And there are many extra fun things we can do beyond. Look at more complex architectures, look at cascaded CDNs, cases where some origins comes with free egress traffic, which is sometimes happening. Also cases where it's a multi-region delivery and you have commits, for example, global commits, but then the prices in each region are different. It becomes a flavor of same problem. And with live, it becomes even more fun. So with this, thank you very much, and enjoy the much-deserved break. Thank you.
All right, thank you.